This is the fourth lecture over quadratic functions for Math 107, Chapter 2. I'll do one more example from the homework, or maybe two. This has to do with the orange trees. Okay, the yield, that means the number of oranges you get per acre, depends on the number of trees you plant, and the equation is written already in factored form. If you distribute the x through, you'll see this is 378x minus x squared. A is -1, so this is a parabola opening down. If it was written in this form, you could easily factor it, but it's already given to you in factored form, so we'll just use it. So I want to find the roots. When it's in factored form, go for the roots. X, 378 minus x. Alright, I set each factor to 0. So the first one is going to be x1 equals 0. I set that equal to 0. Then I set this to 0. 378 minus x equals 0. That gives me x2 is equal to 378. Okay, at these two times I get no oranges from my orange trees. Why? You don't get any oranges at x1 when it's 0 because you didn't plant any trees. X is the number of trees per acre you planted. At 378, according to this equation, you'll also get no oranges. The reason is that you've planted them so densely they crowded each other out, and as a result you didn't get any oranges. You want to find the number of trees per acre that will give you the maximum yield. Well, that would be the peak of the vertex, and where's the h value? It's halfway between those two, so all you have to do is add those. 0 plus 378 divided by 2, and that gives you your 189. To find out how many trees, what the yield is actually going to be, how many oranges you get when you plant the 189 trees per acre, you put the 189 back into the original equation. In this case, the yield will be k when I put the 189 back in, so I'd have 189 times 378 minus 189, and that will give me the number of trees per acre, or number of oranges per acre I will get at the peak. And the equation, of course, will look something like this. You'll have your 0 here, your 378 is over here. That's your peak right in the middle between them at 189, and you go up to like 35,000 or something. At this point, because this is h, that's your h and k, there's your vertex. You determined it was opening down by that, because a was equal to -1. I worked through most of the problem on the quadratic break-even analysis in the lecture on the homework, so now I will just summarize what we know about quadratic functions. There's a lot of little pieces, parts, but by using the ones that are available to you, you can get some insight and minimize your work at the same time. This is much better than just plugging numbers in, getting something out, and then just moving on. So we're talking about quadratic functions, quadratic equations, They can be written in two forms. One is the ABC standard form, ax squared plus bx plus c, and the other is a graphing friendly form, x minus h squared, a times x minus h squared plus k. The a is the same in both equations, by the way. Things that you're looking for the parabola is you want to know if it opens up or down, and that's determined by the sign of a. If a is greater than 0, it opens up. If a is less than 0, it opens down. So you can establish that right away on both equations. The next thing you're looking for is the vertex, not in this order, but another point you're looking for, and that's denoted by h and k. If you have the graphing friendly form, you can read it off, right, of the graphing friendly form, hk. If you don't have the graphing friendly form and you have the ABC form, you can still find it because, as I pointed out, the first term in the quadratic function is h. h is equal to minus b over 2a. That's one way to find it. The other way to find h is if you happen to know the roots, you can average them, and there you found h. So there were two ways, actually three ways here to find h. One is to read it off the equation if it's given to you, if you have the graphing friendly form. If you have the other form, you can compute h as minus b over 2a. the first term in the quadratic function, or as the average of the roots. So now you have h. If you want to find k, you have to put the h back in the equation. So whatever you find for h, you'll put here, x squared plus b times h plus c. And now you have h and k in both cases. The other item that we're looking for are the roots. So the roots are the values of x where the parabola crosses the x-axis. There are three types of roots. Two real distinct roots, two real equal roots, and a complex conjugate pair. So there's always going to be two roots. I'm going to write the quadratic function here because we're going to pick a piece of it off. And the part in the quadratic function that determines what kind of roots we have is b squared minus 4ac, the discriminant. If b squared minus 4ac is greater than 0, you have real distinct roots. If b squared minus 4ac is equal to 0, then the roots are also equal. If b squared minus 4ac is less than 0, then the roots are complex conjugates. So that gives you a little heads up as to what kind of roots that you're going to have. Now to find the roots, there's three ways to do it. You could use this quadratic function here and plug into it, or you can factor, or you can complete the square. Only factor if it is easy, and the easiest cases are those in which there's no constant. If I have y equals ax squared plus bx, just factor out an x and then set each factor equal to 0, and that will give you your roots. And here's a look graphically at what these roots, how they appear graphically. So I'll do three cases here. I'll do always downgoing parabolas. You can translate it easily to a parabola that opens up. So here are your three types of roots. Okay. If you have two real distinct roots, the parabola crosses the x-axis in two places, two distinct places. If you have two, these are two distinct roots. If you have two equal roots, then the parabola just hits the x-axis at its vertex. In this case, here's x1, x2, and the h is halfway in between them. Okay? In this case, x1 is equal to x2, and it's also equal to h. In the third case, the parabola never hits the x-axis. In this case, the roots are complex conjugates.